name's Joe Rollin. I'm a former ARPA-E fellow and current special government employee with the agency. Each year, 50 million tons of wet wastes are left to decompose. Streams rich in chemical energy, like organic residues and manure from animals, often stored in ponds, as depicted here, cost farms and businesses significant disposal fees. In addition, they produce biogas as they decompose. Biogas is composed of about 60% methane, about 40% carbon dioxide, and contains a number of trace gases as well, such as hydrogen sulfide. Most of this biogas today is not captured or flared, and so personally, my family's from Montana. I've spent a fair amount of time there, and I appreciate the smells of the ranch and the countryside as much as any of you. But the fact is, this is a legitimate health hazard, and in addition, it's a significant source of greenhouse gases. Today, I'd like to talk to you about, instead of producing these greenhouse gases, producing fuel. The opportunity is significant. When we consider all of the wet feedstocks that we can convert, there's the potential to displace all oil imported from OPEC countries. So the question is, can we do this cost effectively? Currently, the answer is no. Liquid biofuels production technologies require sterilization as an initial step, and wet feedstocks simply are too expensive to sterilize, and this is both energetically and financially. There is one means of converting wet feedstocks, and we call this anaerobic digestion. We simply put the wet feedstock into a bioreactor, and in the absence of oxygen, it again decomposes to form biogas, and that's our product. Globally, this is done extensively. There are hundreds of thousands of anaerobic digesters in operation worldwide, from 3,000-liter farm scale to 5 million-liter industrial facilities. In the US, however, only about a third of these resources are currently utilized in this manner. So what's preventing their further implementation? Well, when we look at this as a process, it's quite simple. However, due to the distributed nature of these resources, as shown here, this is from a recent Department of Energy BETO report on waste streams, and the requirement to purify the methane and especially remove sulfur-containing compounds before it's added to the natural gas infrastructure. In most places in the US, natural gas simply cannot compete on price with natural gas. So where might we look for inspiration on how to convert non-sterile, high liquid content feedstocks into value-added products? It turns out the cow has been evolved to solve just this problem. The cow's combination of grinding and regrinding the feedstock, compartmentalization of function with its multiple stomachs, use of an evolved microbial community in these stomachs, and in situ product separation comprise a model bioreactor. Furthermore, much as in our desired process, cows don't want to produce biogas. This represents for them a loss of nutrients. And indeed, in the cases of the healthiest cows, they don't produce biogas. Looking back at our process, one metric is immediately apparent. In the best anaerobic digesters, we can achieve rates of about 5 to 25 grams per liter per day of productivity. Cows are an order of magnitude faster. So what are some cow strategies that we might be able to harness in designing a better system here? First of all, we could look at ways of modulating the microbial community that's present in our bioreactor, learning from host and microbe interactions in the cow, for example. Now, this has been done for years through the modification of process conditions, such as pH, temperature, and hydrogen partial pressure. But recent advances in microbiome science offer new means of monitoring and predicting how the microbial communities behave. In addition, there are further means of modulating the biochemical pathways, which could include engineering inocula to be feedstock specific, as well as the addition of enzymes, or potentially even phage control. And these are viruses that can interact with the microbial population. In chewing the cud, the cows grind the feedstock after an initial biological pretreatment, which results in a highly energy efficient means of increasing their conversion rate. So perhaps co-treatment offers us opportunities in our reactor design. Finally, healthy cows absorb organic acids through the lining of their stomach before these can further degrade into biogas. Likewise, the use of membrane separations plus downstream chemical upgrading offers us the opportunity to produce liquid hydrocarbons instead of biogas as our final product. And if we can achieve hydrocarbon production at the same rates that the cow achieves, there's the potential for the same farm-scale bioreactor that today produces only $10,000 of biogas to produce $500,000 of hydrocarbons. Beyond Biogas aims to significantly increase the cost effectiveness of wet feedstock conversion. In addition to the waste streams that I've discussed today, this also ties into a nascent ARPA-E program called Mariner, which seeks to cost effectively produce macroalgae. And beyond biogas, we seek to harness innovative reactor design, advanced understanding and control of microbial communities, and integrated product separation. And in doing so, dramatically reduce our oil imports, reduce a source of significant emissions, and provide economic opportunities in both rural and urban areas. Please join me in learning from the wisdom of the cow, and in doing so, help enable the circular economy. Thank you. Next will be Mark Von Keitz, Program Director.
Joe, thank you very much. And welcome, everybody. It's a great pleasure to be here to talk to you. And I would like to continue the theme on methane in a way that is a new program idea. It's still very, very early stage, but I just wanted to talk to you a little bit about, even if Joe's program were to be 100% effective, there's still a lot of methane going to be around. And that's in particular due to the great advances in fracking technology. So the issue with methane has really been, natural gas has really been becoming, how can we maximize the benefits that we can get out of this big US natural gas wells? And ARPA-E has actually been working over the last few years on a variety of programs to engage natural gas resources into a variety of energy spaces. There's MOVE with new ways of building tanks that allow you to use it better in vehicles. Gensets is combined heat and power driven by natural gas. The remote portfolio has been looking at biological ways of turning methane gas into liquid fuels. And today I wanted to talk to you about a new idea on gas to gas and solid conversion. So to start out, if we look at the methane molecule, 4 out of the 5 atoms in that molecule are hydrogen. That is only about a quarter of the weight, but 50% of the energy. And if we are able to take this energy and convert it in fuel cells into electricity very effectively, it's a great way to power mobile applications as well as stationary applications. So it's really looking at the methane as a source of hydrogen. And it's not really anything new. We have been doing that and actually doing it on an everyday basis using a process called steam methane reforming. And it's used for the Haber-Bosch process that we heard earlier in the other room. It's used for every day for petroleum refining and even for gas to liquid type processes. The challenge with this steam methane reforming is that, first of all, it really only is economical at very, very large scale, which makes it difficult then to distribute the hydrogen, especially for applications in the transportation space, and then there are significant CO2 emissions associated with it. So today, I wanted to talk to you about an alternative approach to abstracting the hydrogen from methane that's called thermal cracking. It's not really a new process. You can go back into the literature, back to the 20s and 30s where it's first mentioned, but it might be an idea worthwhile revisiting. And so what you do at very high temperatures, you really crack this molecule into hydrogen and into solid carbon. So what does that really mean then with regard to, in comparison? We can either steam methane reforming, we make CO2, and there for 1 quad of hydrogen, this is 10 to the 15th BTU of hydrogen, of energy in hydrogen. And so for steam methane reforming, we have 70 million metric tons of this material, or that's 117 million cubic meters. So it's a very, very significant amount. And this is at a pressure of 1200 psi. So, okay. By contrast, the solid carbon is still a lot of material, but it is less. So it's 22.3 million metric tons and 45 million cubic meters. Once again, getting an idea what the size is. This is a cube of a size that has 2 football fields on the length of the cube, and that is including the end zones. So the question then really is not so much just the volume, but what is really the value? And so with CO2, we know that right now, for the most part, the value is 0 if you just let it go up into the air. If we are able to recover it and put it into oil wells for enhanced oil recovery, the cost is maybe $40, or the price that we can catch is about $40 a ton. If we are thinking about wanting to capture this and store it, there's definitely a negative value associated with this. By contrast, let's look at carbon. So in some ways, we can look at it as a minimum level of cost for $100 of metric ton metallurgical coal. Carbon black goes into the thousands. Carbon nanotubes, millions. And if you want to really get fancy, you go to that level of carbon. But I just want to let you know we can't do that one quite yet. So, and then really the question becomes, it's not just dollars, it's also the market size. And so one of the things that I wanted to remind you, 22.3 million metric tons of carbon for 1 quad. That's about 1% of US energy consumption. So to put this material away, you have to look into markets like polyolefins, steel, concrete. So you get very close into the building technology market. But when you go to the level of concrete, you have to ask yourself, well, what I'm competing with, mostly sand and dirt. So it's not quite that easy. So we have to get some match on the value side. Nonetheless, I think the building materials market is still quite interesting. And so here are some examples of carbon-based materials that by themselves can't maybe be at the level of price of concrete, but they may enable the building of still low-cost houses because you can prefab them. And so this could be a potentially very interesting way of utilizing these materials at very, very large scale. So you actually use then building products as alternative CO2 sequestration processes. One potential path for this is go from methane to carbon nanotubes. And while this is clearly not an advanced process, there is evidence that this is a route that is possible. And so there is a group at Rice University that has then taken the carbon nanotubes and produced fibers from it that they can then make materials with. So it's really one potential route that may enable this kind of utilization on a large scale. But no matter what type of exact product we are going to make, we will need a process that delivers products that really meet performance targets, that provide sufficient yield to really pay for this process, and ultimately is scalable. And scalable means scalable to the right size that we need. Large enough, but also that it can hopefully be deployed in a distributed fashion. Some of the enabling technology developments that we see in this space is molten metal reactors, plasma arc reactors, really advances in computational fluid dynamics to better understand reactions in this space, and also the molecular modeling environment that gives you a better understanding of some of the molecule growth that we would envision. So the next step is a workshop that we hopefully will have sometime this summer to bring together experts in catalysis, process engineering, material science, as well as product application and development. And really, these teams, these different groups, hopefully will be able to better define the best opportunities in this space to turn methane into a material that's hydrogen and a very valuable and broadly applicable carbon material. If you're interested in this, please see me here after the presentation or during the rest of the conference. You can also email me, and I really appreciate your time, and thank you very much. And with that, it is my great pleasure to introduce my fellow program director, Eric Schiff.
All right, we'll give a moment for the first slide to come up. Large green button, right? Gentlemen? There we go. Actually, we're now, I see, it was memorizing it. Okay. So good morning. I'm Eric Schiff, Program Director at ARPA-E for the last 2.5 years. I've been working on a couple of major programs. One is solar energy conversion, and the other is building energy efficiency. Today, I'd like to talk about a hybrid of those two ideas in building integrated solar power. This is a picture of the Rome Trade Fair, an installation from about 2009. Those blue bands you see are solar cells. They're generating about 1.4 megawatts of power for the Rome Trade Fair at maximum nominal capacity. The Rome Trade Fair is in Italy, of course, but the solar cells on the top were manufactured by Energy Conversion Devices, which is a US company. That was an export business. I know a little bit about them. I collaborated with them for about 20 years, and I'll tell you a little more about the sorry end of the company in a second. But an installation like this has to serve two masters. So the first is the architect, and the second is the accountant. As you know, they're often in conflict. But this structure to an architect, I think, is pretty satisfactory. First of all, and perhaps most important, the blue bands are nicely integrated into those curved roofs. They look appropriate, they look good. Second of all, the integrity of the building is not compromised in any way. The actual solar cell technology, the module technology used here is better roofing material than innate roofing material. So this was a success for the architect, but it wasn't so successful with the accountant. What I like to call the solar premium, what you have to pay extra versus a conventional roof, was large enough that the payback was slow, and as a result, companies like Energy Conversion Devices and quite a long list of others who tried this business went out of business about 5 years ago. So let's drill down a little bit more into the story and see what the opportunities for the future in this space might be. The left-hand picture is what you'll see most commonly around today, building applied photovoltaics. You basically take existing modules, such as could be used in utility-scale photovoltaics, and you bolt them on to the roof, and that's actually a pretty good market. On the right, it's like the Rome Trade Fair and this building integrated solar cells or photovoltaics. They've been woven into the fabric of the building itself. And this may not be a perfect example, but it's a pretty good example of how that appearance and integrity change. Now, as I mentioned, the building applied photovoltaics are actually a pretty good business these days. About 120 million square feet of roofing were installed in 2015. The numbers in 2016 will be about the same. That's a nice business. It comes out to about 2 gigawatts or $6 billion per year. The building integrated business is rather small, so instead of looking at that, consider the fact that although 120 million square feet sounds like a lot of business, there are 13 billion square feet of new roofing materials installed every year in the United States, more than 100 times larger. There is a vast, as yet untapped market for integrating buildings and solar power. Now, the building applied is weak on appearance. It's, if you may like it, but many people don't, the bolted blue on. And the integrity requires a good installer. You're making a penetration through your roof. If you want to avoid water leakage and things like that, you're going to have to use a good installer. On the other hand, due to the lowering cost of modules and the increased learning of the installers and other individuals in the business, the payback in a more or less honest way is about 10 years in California for this, which is an acceptable payback period for most building owners, a little bit on the top end. The investment tax credit's been important to the success of that business. On the right, appearance is great for potential, the integrity is great for the building integrated, but the payback is unknown. It's worthwhile going a little more deeply into the economics of this business. So what we'll do is analyze the solar premium, the maximum amount you can expect a building owner to pay for the solar power that might be generated on the roof. To do that, you have to assume no compromises on appearance, all right? Otherwise, you have something that's impossible to cost. And the integrity of the roof better be no compromise as well. And that rule of 10 payback of 10 years needs to be followed. So building applied photovoltaics, a successful business right now, the price per square foot, an unusual way of pricing it, is about $45. Building integrated price premium, that's how much extra it should be worth to a building owner to put solar on the roof, has to be lower than about $40 to make a business. This is because to preserve the aesthetics, you're going to have to take a hit on efficiency. But other than that, you don't necessarily take any hit. Now you need to compare that to what the synergies might be. So what is asphalt shingle, the cheapest, most common roofing form, take? It's about $5 a square foot. So if you add the two together, you might get away with charging $45 a square foot for a solar asphalt shingled roof. But you can see that the synergy possible between $5 and $40 just isn't large. On the other hand, slate roofs, that's about the premium type of roofing that people are willing to buy in wealthier neighborhoods for a nicer look. That's about $20 a square foot, and there you see there is an opportunity. Synergy that could lower the price of the solar enough to make the business go, and indeed one prominent company is interested in exactly that market sector. Now the middle case, where you might look for opportunities that I think are untapped as of today, is something like standing seam metal roofs. Attractive. There's actually an example right out the door in the garden area next to this where we are, where the technology showcase is now. So there's an opportunity there at $10 a square foot for trying to mine a synergy and take a look again at the market, which of course drove many companies that tried this experiment about 5 years ago. Well, one thing that's changed is the fundamental cost of the photovoltaic technologies has come way down in the last 5 years, as probably everyone in the room knows. Crystalline silicon, cadmium telluride thin films, even SIGs is a possibility, and of course there is the dark horse racing along fairly impressively so far of perovskites, but we'll put that into the future a few years. So those are all the advantages that would allow us to consider it again, but there are certain constraints that we need to obey. First of all, again, how low a cost can we integrate the PV for the roofing is? There are new technologies, the modules are cheaper, the installer base is better, so the opportunities are definitely there. And then there's essentially an untapped opportunity, which is the optics of building something like building integrated standing seam metal roofing needs to be good. So we accept no compromises whatsoever on appearance. This means homeowners want, if you go to a roofing store, you've got dozens of possibilities. And in addition, not all of your shingles are going to be solar, but you, from the street, mustn't be able to tell the difference between the solar roofing and the non-solar roofing. So I think that's a promising area that's really untapped at the moment. So let me conclude by talking about ARPA-E and building integrated photovoltaics. There are two main opportunities. If you have exploratory ideas that you think could galvanize investment in this area, we have a small project ideas program. And then, of course, as was mentioned earlier, Open 2018 is looming in the future, we hope, about a year from now, which is for major funding. So thanks for your attention. If you're interested in this area, let me or one of the other program directors hear from you. Thanks. And it's my honor to introduce Jenny Gerby, who will give the final presentation.
Just to remind you to text those questions. We've seen 3 amazing fast pitches, and I'm sure there's a lot of questions out there that we can go over in just a minute. I'm going to talk about Sensor, which is a funding announcement that's actually open right now, and I'll talk more about that in a minute. But first, I want you to think about right now what is going on at home for all of you. If you're like me, you might have cats with unique personalities that are doing very stupid things. Maybe you have a dog. But think about all those times you're here and you're not at home. Your home is empty a lot of the time. And we heat and cool those houses way, way more than we need to. This is a very old problem. Thermostats have been around for a long time to try to solve this problem. But somewhat shockingly, all of the technology we have to have what used to be a supercomputer in our pocket, we still don't use electronics to actually reduce the amount of energy we're using to heat and cool our homes. We have more efficient systems, we have better control schemes, but at the end of the day, if it relies on a person to program that thermostat, studies have shown that that does not make an impact in energy usage. This is a big deal. We need to find a way to do this without having to involve the humans at all. I certainly would like one less thing to think about, and I'm pretty sure that you all would too. So let's think about a slightly more complicated situation. What happens when you're not at work? So this is one of the buildings in the office plaza where ARPA-E works. And let's think about that building for a second. It's a big open plan building. That building is heated and cooled and ventilated when nobody is there. There are probably not a lot of people there right now because we're all here. Is there anything different about that building today than there was yesterday or the day before or the week before? Not really. There's a lot of energy being used in this, and we do not do a good job of trying to save energy in this space. And there's some really good reasons of why it's difficult. We have some mild temperature setbacks during the weekend when we know it's not going to be occupied, but that's really all we do. So let's think a little bit about energy. You heard Mark mention a quad, and a quad is a very, very large amount of energy. And we use 100 quads in this country for everything. Every fuel, transportation, manufacturing, all of it is about 100 quads. Okay? 13 of those are used to just heat, cool, and ventilate residential and commercial buildings. Not industrial, not manufacturing, none of that. Just commercial buildings and residential buildings. And that is an extremely large amount of energy. And we are going around killing ourselves trying to fix our grid, trying to find more ways to get energy, trying to reduce our energy imports. And we have this staring us right in the face, and we're not using technology to solve this problem. I want to use technology to solve this problem. So what do we need to know? Your house needs to know if there's somebody in it or not. Relatively simple. We do not want to know who you are, what you're doing, or where you are. If we had this, we could save 30% of the energy that we use. And obviously that's nice financially, but I'll tell you who's excited about this are utilities. Because if you want to use things like demand response programs, there's a much higher consumer adoption if they know whether or not somebody's home so that they can trigger whatever technology that's going to be. So this actually has a lot of value, and it sounds so simple, but when you look at what the accuracy and performance of these things would have to be to enable consumer adoption, we actually don't have this technology yet. And there's a lot of people that are ready to use this technology. So if we had this enabling technology, it could be used in the marketplace right now. And that's really exciting to me because we're all about impact. So let's go to this work situation then. So this is a little bit trickier. You can't turn the thermostat up or down relatively quickly like you can in a house. That building takes a while to heat up or cool down. But you can change that ventilation relatively quickly. But the problem with changing ventilation is that it gets a little bit scary because you can't see it. So there's our office building. We have a couple happy people working on the ARPA-E floor. And then the next hour, this happens. Now you have hundreds of people on another floor. We don't treat these floors any differently right now. And if these floors are each an HVAC zone, you would want to treat them differently. You would want to treat them differently to save energy, but you would also want to treat them differently to make sure there's appropriate indoor air quality for that floor that has 300 people. This room is ventilated at 100% when we're not in it. And that's ridiculous if you have the ability to change it. And we actually have systems in most buildings that could use this information right now. But what we need, what we need to know is which HVAC zone people are in and how many people are in that zone. Yet again, we do not want to know who you are or what you're doing. And in fact, we see this as a big adoption barrier, this issue of privacy or perceived privacy or things like that. So that's something that technology can help solve as well. So if we had this, we could save 30% of the energy we're using conservatively, mostly by looking at this untapped ventilation resource. Now, this is a challenge because everybody wants more ventilation all the time. And people are doing some really interesting studies to show lowered productivity and cognitive impairment at CO2 levels that are lower than previously appreciated. This is a big deal because when you think about the value in a building, the amount you pay for energy is down here. About 10 times higher is the actual price of the space of the building. 10 times higher than that is the productivity of the people in the building. When you start talking about emphasizing and maximizing productivity, people start to really care about that and really listen, and that's really valuable. So if we had a way to have an indicator that the ventilation was actually working the way it's supposed to, that would be very valuable. And we identified that as a key adoption barrier. You can't go around putting in a system that changes the ventilation if you have no way of having an indicator that it's working. Having cheap distributed CO2 sensors is a way to have an indicator that your ventilation system's working. It's not measuring everything you need to measure for air quality, but if your ventilation system's off and there's people in there, that CO2 will go up. We don't have a way right now that is cheap and easy to use and easy to install and everything like that. We have some that are actually quite expensive and they have trouble working over time. So that's something else that we need. So when we think about putting together a program at ARPA-E, we keep emphasizing impact, which can be difficult to do when you're talking about technologies that don't exist yet. In this case, we think about technologies that are out there that would help this come along, like very low power electronics, systems on a chip, new solid state sensors, things like that. I think that from a technology point of view, we are really poised to be able to solve this problem. We just need that push, that time, that money, people focusing on the problem to be able to do it. But in order to be successful, you need those technical metrics to be influenced by those customer requirements. And who's the customer and who's the buyer can be completely separate things too. So you really have to think about that, have these things all influence each other, and oh, by the way, it needs to cost a certain amount to make sense to buy as an energy-saving device. You have to solve all three of these things in the metrics that you put in a funding announcement. And ARPA-E is the type of place where we can do this sort of thing. We spent a year putting this program together, a whole team of people, to come up with metrics to be able to do this. We talked with everybody from people that actually invent these types of systems on a chip technologies to building owners and architects and builders. So the structure of this funding announcement, you can go on the ARPA-E Exchange page, just Google ARPA-E Exchange, and it'll come up. Look at the sensor FOA, you'll see 4 sections. Residential binary sensing, which I talked about, this commercial people counting need. The CO2 sensing has its own section because we think it's so important for the adoption of this technology. And then testing and validation development. That is also important to prove how much energy you can save so that somebody has the ammunition they need to adopt a technology like this. They're all individually in this FOA. So if you are interested, there are 2 more weeks to submit a concept paper, which is only a few pages, to this FOA. We then go through a review process, and then we invite full applications, and then there's another round after that. So please, if you're interested, take a look at this. Send it to your friends who might be interested in it. Whether or not you're in the lab putting together electronics or you're a potential end user of this technology, we'd still like to hear from you. Okay? Thank you very much. And now we're going to, okay, put that mic back. Now we're going to go to some, we have quite a few questions on here, which is fantastic. Thank you very much. So I'm going to ask some questions of some folks here. let's see. Hold on. Sorry, I have to read, and I'm old, so I have to take these off. Okay. Let me ask Eric a question about BIPV. Are there opportunities to improve thermal management of PV by going to BIPV?
Sorry.
So I'll ask that again. Are there opportunities to improve the thermal management of photovoltaics by using them in BIPV?
I'm sort of guessing what I think the question must be addressing. One trouble about roofing is that it's hot up there, which causes a decline in the efficiency of your solar cells. So you lose value. That was envisioned in this section I called optics. Proper management of the optics of the solar cells, not only for appearance, it manages excess heating by the unused infrared part of the spectrum and heating in general. I'm not sure that captured everything the questioner asked, but that's a reply.
Okay, thank you. And I have a question here for Joe. What are the mass transport challenges and/or advantages associated with what you are proposing?
Great, thanks. First of all, briefly, I didn't mention this explicitly in the pitch, but this direction is something that we've been exploring at ARPA-E. We ran broadly, the entire Beyond Biogas concept. We ran a workshop on this topic in October of last year, and we are planning to release an RFI at the end of April. So that's a good way for you to provide us more feedback. Also, please talk to me after. And the RFI, or request for information, would be released also on the ARPA-E exchange, like Jenny mentioned. Okay, so on to the question. So mass transport challenges are definitely, that it might be the fundamental challenge of this approach. The advantage, of course, of biogas is, as a gaseous product, it simply phase separates out. That doesn't happen to a complete extent, actually. Often at the temperatures where anaerobic digestion occurs, a significant portion can remain dissolved in the liquid phase of the biogas. In our case, however, it's even more challenging. Either we are using membrane separations, or there are some alternative ideas, such as producing a volatile product where you can preserve this type of strategy. But I think the separations technologies and that component of this will be really important if we do want to achieve the liquid hydrocarbons out as an output.
Thank you. I have a question here for Mark. What do you view as the primary technical challenge to be solved to enable your concept?
I think the primary challenge is to make sure that you create a meaningful product on the carbon side. So that means that you really have something that has appropriate properties for an application that has a large enough market. And so I know that I'm pretty vague on that. So as I said, the one idea that is out there is to make carbon nanotubes. So really being able to make this material in the appropriate quality at an appropriate yield, or some other related product. And we are really looking for getting ideas from you guys, from the community, what we should focus on, and that will be something that will also be explored in the workshops that we hope to have this summer.
Thank you, Mark. I have another question here for Eric. Can you elaborate on what's needed for optical coatings for BIPV?
Well, that would continue the previous question. It is actually tricky because you want to create an appearance without wasting any light. So that's one aspect. You'll probably have to sacrifice something there. And then in addition to that problem of what's the minimum amount of light you have to lose to create the appearance you want, you also do want to do thermal management in the infrared by cutting away the wavelengths that aren't going to be useful that might turn into heat otherwise. And there's also the exotic possibility of trying to put in optical cooling mechanisms, a very clever idea that was actually supported by ARPA-E and is going to commercialization. So you actually try to cool these things innately by adjusting the optics in the deeper infrared. So there's a lot that can be done there. It's a bit untouched as of the moment.
I'll go ahead and answer a quick question for myself. Somebody asked, what percentage of current commercial buildings are capable of moderating ventilation in discrete zones as would be desired by sensor? That's a very good question, and we actually break this down in the funding announcement, and we actually do it by sub-market. So for example, medium to large commercial office buildings versus academic versus other type of buildings. And in office buildings, medium and large office buildings, a number of years ago, that number was already 80%. So that number is higher than that now. So actually, it's striking how many buildings have that ability to be able to do demand-controlled ventilation and actually don't use it. So it's really an untapped resource right now. So thank you for that question. I think I will ask Mark another question here. Are you interested in the idea first focused on methane capture prior to conversion? Is that of interest?
So when you say first capture methane, I'm not quite sure what the question is exactly going at. I'm assuming that it's capturing methane from an additional source. So the assumption at this point is that it would be methane that comes out of the natural gas distribution system. That's really the primary source for this process that we envision, because especially from a hydrogen perspective, you would leverage the natural gas pipeline system to distribute the gas widely to more distributed processing locations to minimize the need for building a separate hydrogen infrastructure on a large scale.
Very good.
That answers the question.
Okay, that's good.
Thank you.
And I'm going to go ahead and I will ask Eric one more question that some people might have on their minds, and I think we can answer it in the question section. What's your view of Tesla's announcement that they'll be selling building integrated roof tiles with PV, and will they meet your solar premium criterion?
Well, we'll find out soon if they meet my solar premium criterion. It's not announced yet. But it's what the company is doing is sort of repeating the success for electric cars in the roofing sector by going to the highest end slate tile type of roofing where the synergy is the largest, which I think is actually a pretty smart strategy. So there are a number of subtleties to it. What they can assemble these tiles and install them for, your guess is probably as good as mine. But if they don't meet something like the criteria I showed you, then I'm dubious they're going to have much of a market. So it'll be very interesting to follow. What I hope happens is that, somewhat like the Tesla electric vehicle, this will act as a first market. Relatively wealthy people who can afford it and want it as a status symbol, if you like, in addition to its payback, and thus create the infrastructure for a more widespread and greater energy impact market, where perhaps something like the standing seam metal roofs would be the opportunity.
Thank you. And one very brief last question for Mark. What is the efficiency and energy cost of the transformation of methane to solid carbon?
So usually you recover about 50% of the energy content of the natural gas in the form of hydrogen. That's really the number that's out there in a variety of analyses. It's about 50%. And so you definitely leave a certain amount of energy on the table by not burning the carbon. But if you are looking at the energy that it costs you to take methane to hydrogen via steam methane reforming, that's usually 75% efficient. But when you then add carbon capture to it, you're about at the same level. So it comes down to, what do you rather deal with? Large quantity of CO2 or large quantity of carbon? And there it comes into play, what type of carbon are we going to get? And that's really the space where I think we would play in with this kind of an funding program.
Great. Well, I want to thank our presenters and thank you all very much for coming to the session today.